down to nanokelvins. Another important aspect is interactions and the possibility to tune the interactions in a broad range from negative to positive effective interactions, which is done via so-called Feshbach resonance, which was introduced by Hermann Feshbach when he was studying nuclear reactions. So this kind of resonances in scattering length usually appear when there are two or more channels for particles to interact, and if these channels are cupped, so there are open and closed channels, depending whether they can accommodate a bound state or not. And they are cupped, in this case, by hyperfine interaction of the atoms. So these are the triplet and singlet channels. And bound state is, of course, in singlet channel. So, and the energy levels of between incoming and the bound state can be tuned by magnetic field, because the triplet state can sense the magnetic field, so its energy can be changed. And the scattering length, which is plotted here, is changed from positive here to negative here, and here is the magnetic field. So there is some kind of resonance at 834 degrees. And if one is interested in low density and low energy situations, one can approximate interacting potential between particles as a contact interaction in the S-wave regime with this kind of pseudo-potential when only one parameter is relevant here, which is scattering length, and this is which is tuned by magnetic field. So as you can see, effectively the interaction can be either positive or negative, depending on magnetic field applied. So this will be very important, that it is possible to tune. So one more aspect of the slide will be actually how to really make it resemble the condensed matter systems, like lattice type models. And this can be achieved using optical lattices, which are standing waves made of counterpropagating laser fields, and they act as a periodic potential for atoms. And in particular, one can have different type of geometries. So one can have like three-dimensional lattice, the usual one, and then one can also apply 2D optical lattice in this manner to define 1D tubes, which I'll be mainly discussing in the subsequent cases for fermions. So, I mean, from I think it's since realization of BEC, it's almost 15 years, a bit over it, I guess. And there are quite many experiments actually have been realized in this in this system, so which are kind of listed here. So what I will be interested in mainly about Lagrangian liquid physics for repulsive cases and FFLO physics for attractive cases, and a little bit about disorder in these systems also. So let me go a little bit more in detail on how this reduction happens in 1D, let's say. So this is a Hamiltonian, which has a kinetic energy, this is a potential energy, and this is interaction between particles. And this trapping potential is has like two pieces, let's say. One is a global potential, which defines this ellipsoid, and then this periodic part, which is coming from the optical trap, and which defines the array of tubes, which are quite many in this case, because the lattice spacing is basically half of the wavelength of the laser field you are applying to it. And if the energies or the temperatures, which one is interested in, is between this range, which is a transverse level spacing and, the longitudinal level spacing and transverse level spacing, then one basically occupies a single transverse channel, and one can effectively talk about 1D case. And one more important thing is that because of this confinement in the transverse direction, another type of resonances appear for the scattering length, which are so-called confinement-induced resonances. And this is this part where the 3D is the usual S-wave scattering length, and then this extra piece is a resonance due to the confinement where A transverse is the transverse length of the transverse harmonic length of the tube for individual tubes. So if there is no tunneling between tubes and the optical lattice is deep enough, so these tubes are basically non-independent to each other. So what I'll be talking about in case of fermions is for repulsive interactions, how to realize. Also, they all talk about the paradigm metallic system, Latinger liquids, and how different regimes of this Latinger liquid can be realized and how they can be measured. And for attractive interactions, I'll be interested in properties of the periodic states and what if I can say anything about 1D analog of the FFLO state in the systems, and if it's possible to get the phase diagram of a uniform system from the trapped profiles of the real experiment. Let me briefly tell you about what is usual spin-coherent Latinger liquid. So as you know, in the higher dimensions, like 3 dimensions, the system is all described by quasi-particles, and they behave like ordinary electrons with effective mass, and there are some few parameters which one can then fit to the experiment. But this is different in 1D case, where there are no quasi-particles. It means that this quasi-particle weight vanishes, so there is no pole in the Green's function. So, and all the correlators actually are power laws, and there is so-called spin charge separation and suppression of density states at the Fermi level. So these are the really very important properties, and this one can really achieve doing so-called bosonization of the 1D systems in this like small shorthand notations here. So one can basically map the strongly interacting fermionic system into the weakly interacting bosonic system. In this case, basically non-interacting bosonic systems of different species, charge and spin, which encode charge and spin density fluctuations of the system. Basically. So which have different speeds. That's why there is a spin and charge separation, because all these collective excitations, they carry different, they propagate with different speeds. So that's an ordinary coherent case. So what is the coherent?
What is this G2?
G are they are encoding the interactions between fermions. These are the coupling constants of different processes, which are forward, backward, and so on. And they are labeled some nomenclature to describe those. So what is the distinction between spin coherent and spin incoherent? So usually one is interested in this regime where the lowest energy scale is the temperature. And J is the spin exchange scale, E Fermi is the Fermi level. In this case, it's a standard spin coherent Latinger liquid in a way that spin and charge degrees of freedom both are in principle coherent and can be propagated through the system. So if temperature is in this range. But if the temperature is tuned in a way that there is a big separation between spin exchange scale and charge scale, which is at E Fermi, then spin part of the Hamiltonian basically is decoherent. So there are no way spin excitations to propagate in this system. And what happens that the Hamiltonian is basically the charge Hamiltonian, and the spin part comes into play just the massive degeneracy to the power and degeneracy of the system, and which needs to be taken into account while one does the averaging, which has a profound consequences for the Green's functions, for example. So as I said, in ordinary Latinger liquid, one has collective excitations. They separately carry spin and charge. Both of them are coherent and they're propagated to the system. So if you do some excitations, you will see like spin and charge waves going in different speeds. But in the case of spin incoherent, so there are no spin excitations in the system anymore, only charge excitations, and then there are so-called non-unitary spin charge separations in the system. What this non-unitarity means that the Green's function is no more the power law, but it has the exponential decaying part because of the spin. So this comes from this averaging over the 2 to the power n spin states. So this is the main. So this is only basically this Green's functions, the charged Green's function in principle with some decaying piece of the spin part. So now what we can say about these regimes in a trap. So as you say, I will tell you that the trap is really important here. So I want this cloud to have different densities in different places, which is usually the case. And what I will claim here is that in each tube, both of the regimes will be realized, and depending on the interaction strengths and trap geometry, in a way that in the center, higher density means effectively weaker interactions in this case, and it will be like ordinary coherent regime. And near the edges, density is so small that it inevitably will reach the spin coherent regime because the spin exchange or the velocity for the spin excitations goes to 0 there. So the one can say that in the edges it's spin coherent, in the center it's spin coherent type of things. And I then write the Hamiltonians in different regimes in a way to take into account those non-uniform nature. So those coefficients, velocity and these interaction parameters were before coordinate independent, so they were uniform. So this way it allows to introduce it in the LDA or Thomas Fermi approximation level. When locally I describe the system, so local system responds to the local chemical potential, which is basically defined by the trap potential.
So do you take into account the long-range Coulomb interaction here?
No, it will be, in this particular case, no, but it can be taken into account. It should be modifying, depending what's the range, but it effectively should be modifying those Ks and...
No, I'm asking about, like you have non-uniform electron density.
Yes,
so
but the LDA doesn't really take into account
so
the
you
correlations
see
in a
local
local nature. Yeah, of course, which is an approximation. And this is, in a sense, a good approximation. It's some kind of a WKB type approximation, actually, if one really looks closely. So we have non-uniform systems. So there is something like a trick or some really non-standard transformation which I'm doing here to map this non-uniform system to a uniform system again, but with hard wall boundary conditions. So this is some kind of a transformation for this momenta and these phi fields to map it to the some kind of a standard case, which is a uniform system with hard wall boundary conditions. And this is highly kind of non-trivial in a sense that it's possible, but apparently it looks like it's possible. That it preserves the commutational relationships and everything. And then one can use standard tricks from the conformal field theory to calculate these functions, all the correlations. So that's what we're interested in, is how to observe these regimes, and our choice fell on the so-called density-density correlations, which were introduced first by Altman, Temler, and Lukin, that it can be used to distinguish between different correlated states. And what we'll be interested in is the density correlators, especially off-diagonal ones in this case, so spin up, spin down. And one can really look and calculate those, what I explained in the previous slide. And what one sees is that those Green's functions actually behave differently depending on which regime you are. So if you're in this spin coherent regime, this correlator is always positive. If you are in spin incoherent regime, it's always negative. And if you are non-interacting regime, it's 0. So this is a very good thing, in the sense that what we are looking at here is the very robust observable, because what we are after is the basically average signal, because in the experiment what one gets is the average signal over all tubes. And the robust observable which I will be defining, needs to have high signal-to-noise aspect, signal-to-noise ratio, and should be easily measurable by experiment, and also which comes out is kind of not really a usual correlator one measures in condensed matter. So one not usually goes and measures density-density correlations in the systems. And so that's the average Green's function that I defined before, and it is plotted here, and one says that if one has weak interactions, one is effectively in the spin coherent regime. For stronger interaction, one crosses over to the spin coherent regime, and this black line is, full line is the response from the full cloud, and this dotted line is the response from the central cloud. So if one averages, one doesn't really lose this crossover type behavior. So what one sees here is that if one in this regime, it says that these tubes are predominantly in the spin coherent regime, because some part of the tubes will be coherent, some incoherent. But if you are in this case, one can say that it's predominantly in incoherent regime. And since there is really a distinction between interaction and non-interacting regimes and behavior of the correlator in different regimes, so one can unambiguously say in which regime it will be realized. So in one case, you can say that if it's non-zero, it's interacting, and then if you know the sign, you know in which regime you are. So that's about the positive interactions. So what about the attractive case? So what I'm interested in is how attraction and plus the spinning balance. Because in before the case, what we described, it was spin balance situation. So what is interesting here that there are some exotic states postulated or proposed in these systems, and one of them is so-called Fulda-Farelak-Ovchinnikov state, where the main distinction of this type of pairing is that center of mass momentum of those pairs is not zero like in Cooper pairs, but it's defined basically by the momentum Q, which is the difference between different Fermi momenta. And on top of this, the order parameter is modulated by the same momentum Q. So it has some kind of non-uniform case. And there are quite many theoretical consideration of this models in 3 and then mainly in 1D, what I'll be describing. So there are myriad of different techniques applied here. So what I'll be interested in is Bethe-Ansatz technique in finite temperature, because the experiments are actually done at finite temperature, as we will see. Because it's a fermionic system, so this is one needs to compare the temperature with Fermi energy. And actually these experiments have been realized, and the findings I think are accepted to Nature a couple days ago. So that's very interesting. So let me go first to what one says at zero temperature. So one can go and do zero temperature Bethe-Ansatz calculations or bosonization techniques, as I described before, can be applied here also. And what one says from this case is that one can calculate Green's functions again, or the correlator between those pairing fields, and one sees exactly that oscillating piece in the correlation. And there is this long-range correlation. Sorry, it's not a long-range correlation, but it's algebraic. So that's because of the 1D nature of the system. And from the Bethe-Ansatz, one can really pull out the phase diagram of the system, where is the chemical potential and the magnetic field, and then one sees here some kind of partially polarized case which can be identified to this type of regime. So the regime where there is a partial polarization is effectively 1D analog of the Fulda-Farelak-Ovchinnikov state, in a sense. So what I'll be doing is the analysis will go in this following way. So we have a 1D system in a trap. So what I will do again, employ local density approximation, and we'll be solving Bethe-Ansatz equations, thermodynamics locally in each point in the trap. And when all the possible thermodynamic variables can be calculated. So that's a question about, the possibility of the breakdown of the local density approximation, and that has been observed in highly elongated traps. But apparently it's very interesting to know that in purely 1D case, LDA is amazingly good. And that one can really see it comparing the Bethe-Ansatz calculations to quantum Monte Carlo calculations, for example. Of course, there are, some oscillatory behavior because of the finite size, and near the edges of the trap, it's not really reproduced well. But overall shapes and the different kind of phases one observes, it's fairly good comparison. So, and what the technique is, I said, the Bethe-Ansatz. So this is the method which was introduced by Bethe for solving Heisenberg, spin-half Heisenberg chain. And those type of models which are solved by Bethe-Ansatz actually have infinitely many conserved quantities. That's why they can be solved exactly, and their Green's function can be given by this way, and the eigenenergies in this way, where epsilon of k is dispersion relationship, which is different between different models. And those k's, which are momenta, should satisfy these equations, which are the Bethe-Ansatz equations. So all SU2 invariant models have the same, actually, Bethe-Ansatz equations. What is different is epsilon and alpha, which change between different models. So in this case, which I'm describing, is a continuum model, which with particles interacting with k square, kinetic energy. That's what is happening here. If you have, let's say, if you have describing Hubbard, then you get here sines and cosines and different functions, basically, of k. Okay, so let's go a little bit more detail here. I'll try to go a little fast. So this is the part which is a uniform part, which can be solved by Bethe-Ansatz, which is kinetic energy plus the delta function interacting. Yes, this is the trapping potential, which is a harmonic, which I'll be taking care of via LDA. And these are the equations again, the same, which I showed before, just simply introducing exact values for epsilon and alpha. And one needs to analyze these equations and find out what kind of solutions it accommodates. So these are three types of solutions or three types of excitations in the system. These are unpaired particles, these are bound states of two particles, and these are the spin excitations. And if one looks closely, the spin excitations are the same as in the Heisenberg spin chain. So these are exactly the same type of excitations what you get in the Heisenberg model. So what one does then is to solve the thermodynamic. One is to go to the thermodynamic limit, which means that to fix the density and the polarization to a constant, just putting n and m, which n is the number and m is the number of the minority species. And so those numbers are constant, and one defines particular densities in momentum space for each unpaired bound states and spin excitations to define all the possible densities which come up in the thermodynamics, so which are energy, particle density, spin density, entropy density, and so on and so on. And one also defines f functions which are related to the distribution functions. So if you have non-interacting system, these f functions are nothing else than the logarithms of the Fermi distribution if you have Fermions, or Bose distribution if you have Boses. And what one needs to find out what is the equation for those f's. So this will be so-called these thermodynamic Bethe-Ansatz equations, which are derived by writing free energy functional and minimizing it and deriving the equation for f's. So these are the equations, which are infinitely many because this index n runs from 1 to infinity. So these are kind of three types of equations, one can say, for each excitations. And then one knows what is the free energy. One can calculate all the thermodynamic quantities by simply taking usual derivatives with respect to the chemical potential, field, and the temperature. There's some standard thermodynamics in there. But the thing is that it's not possible actually to solve this analytically, and one does it numerically, and then one needs to truncate these equations and do some self-consistent calculations, which is what I'm not going to describe much. If you are interested, you are welcome to ask. Okay, so the question will be, so after I will calculate those different density profiles in a trap, whether I will be able to understand or they map this phase diagram. And one more thing is that usual phase diagram, in a way, is in this one where the x's are chemical potential and the field, but these are not the good variables for those systems. One really needs the variables which can be measured in experiment, which are actually densities and the polarizations in principle. And that's why we kind of transform this graph into different kind of graph, where here is a total density, and here is the, again, chemical potential, but for the majority species, which actually can be measured by measuring the size of the trap. And so here one sees that this is a fully paired regime here for small fields, which is this one. There is a partially polarized case, which is this one. And there is a fully paired case here, but here it's transformed into a single line because it's basically an equation of state for non-interacting spin polarized particles in this case. Because if you are at zero temperature, this fully polarized gas is non-interacting. So let me describe different regimes actually, what one sees in an experiment. So what one sees in a trap is basically a cut in this vertical cut in this graph. So what happens is that chemical potential actually changes from some value to another value where this is an edge of the trap. So this basically will give you the profile what happens in the center or in the edge of the trap. And it has a little bit different curve here, which I will describe a little later. So let me tell you what this experiment says here. So this is experimental data from Rice University. And here one plots black is the spin up density, blue is spin down, and red is difference. And there are two different regimes in a sense. So for low polarizations, one center of the trap is partially polarized, and the edge of the trap is fully paired, zero polarization. For large polarizations, center of the trap is partially polarized, and the edge of the trap is now fully polarized. And you can just see that it's actually really the case. So here, partial polarization, full pairing, partial polarization, full polarization. So that's what, and the position of the vertical cut is defined by the total polarization of the system. And actually the full lines are the fits, not fits, but these are the calculations from the Bethe-Ansatz. So this is pretty good. So I will give you some other calculations for, let's say, 200 particles with different polarizations here. And here you see total density, here you see polarization. And these are the similar type of graphs which I showed before for experiments, so spin up, spin down, and difference. And you see for low polarizations, as I said, partial polarization and then zero polarization. So there is some critical point where all of the cloud is partially polarized, and then one gets partial polarization and full pair. And of course it's smeared with the temperature, and for us it was important to understand whether these different regimes can be really identified, because they are, you see, smeared. But from our calculation it indicates that if you are less than about 10% of the Fermi velocity, Fermi temperature, then that's fine. So, and apparently experiments in this they managed to go down to from 5 to 10% of differing temperature, which is actually enough to distinguish different regimes. Otherwise, everything would be partially polarized, cloud, smooth, without any distinct features. So to identify those, the boundaries here. So as you see, it gets smeared. So the blue is the coldest and red is the hottest in these graphs. So let me tell you a little bit more about how one actually can take those experimental, or in this case my calculations, to map the phase diagram. So what I will tell you that for, let's say, for low polarizations, actually, let me see if it's here. Okay, let me first tell you for large polarizations how one really maps from this cut to this one. So as you see, this one is the center of the trap. So this is a z coordinate, and this basically corresponds to the center of the value of the chemical potential in that place. And then one changes magnetic, does not change actual magnetic field, so it goes down. And this is the edge here. And this place actually corresponds to this one where system goes from partially polarized to the fully polarized in this case. And the same can be mapped on the other side to those systems where you see that from partially polarized one goes to the fully paired. And this I can really say actually that this actually corresponds somehow to this pairing state, because I see here from the calculations that these are partially polarized states, but it also supports the paired particles. So here is some state which has paired particles and also unpaired particles at the same time. So what is the difference now with this particular phase diagram is that one again can really place these profiles now almost on top of it, because now here I have density and here I have majority chemical potential, and you see this actually this profile can be really placed on top, and you see this is kind of 0 is the edge here as a reference, and then you should read from right to left. So it is fully polarized, as I said, so it really sits on the fully polarized line. And then it enters this partial polarized case until this polarization reaches the value which it should reach, which is about 30%, which is somewhere here. So that would be one way to really have many different this type of measurements, and then place them in this kind of graph, and one should see that all of them should really start fully polarized. Let's say if you are in the high polarization regime, and everything enters in this kind of region. And if one measures total density and total polarization, so the local density and local polarization, one can really map all these isopolarization lines also, because that's actually can be measured experimentally, since they are able to measure spin up and spin down separately, and even the difference they can measure directly, difference between spin up and spin down densities. So this is, and one actually sees that, as I said, if you are not really in a high temperature regime, those boundaries are fairly well defined, so you can distinguish them. Otherwise, everything tends to get smeared, some uniform, non-zero polarization, and actually whole system kind of is a mixture of non-zero polarization and the pairing. So it's not really
can you
clear.
remind me again of what these different lines? What was the blue line and the green line?
So these are different temperatures.
And the lines.
This is the total density as a function of the coordinate of the trap. So that's the profile.
So total density at different temperatures.
Yeah.
Okay.
And so then one can really take, this and because this have the same, basically same axis. So if you go, look at the LDA type scenario, one really just measuring where's the edge of the drop. So what's the size of the system, you can find out what's the chemical potential. And that's, you can basically rescale this Z coordinate into the chemical potential. That's basically how it is plotted on top of each other. And then one sees that the full polarization regime, one enters, one sits on the full polarization line and then enters partial polarization region. And in this case, one sees that one is in the fully paired case and then enters the partial polarization near the center. That's the low, very low polarization regime. And this is actually very interesting because exactly opposite happens in 3D. So that would be some kind of a benchmark whether you achieved 1D regime or not. So in 1D, what happens is the center is fully paired and the edges are partially polarized. And here it's different. And that's will be one of the important things to check, and that's what experimentalists see. Irrespective of that, one can really put this Bethe-Ansatz calculations on top of the experiments as I showed.
So what kind of magnetic fields you test this?
Here, this is not an effective. This is not a real magnetic field. It's an effective magnetic field. Basically, it's a polarization.
Right, but what if I want to reproduce the experiment? What would be?
This actually I'm not quite sure what would correspond to the. So if you
one Tesla is 1 Kelvin, so roughly.
What do you think? You don't really need very high fields definitely here because it's basically this regime is always present here as long as there is no non-zero magnetic field. It depends on in which particle polarization what it is, but in principle there is no a threshold for a magnetic field, which there is some kind of threshold usually in 3D system, but there is no here in this case. So
no, if I want to tune your state by using magnetic field, what field would I need?
I can't really tell you on top of my mind, but we can convert it definitely. We can discuss it. But in principle, there is no threshold. So in any.
But I can move your boundaries by applying magnetic field.
So what you move is this boundary. And then in this particular point, which is a critical point, then this boundary shifts to different type of boundary, in a sense. Yeah, that's a good point. Of course, this kind of propositions to observe this phase is coming from condensed matter, and that has been different. Let's say heavy fermionic systems proposed, for example, to be observed, but there has not been any conclusive measurements to support it. But so some new systems are here. Hot topic is like the organic superconductors, which may have those phases, but it's still not very conclusive. Some kind of like Bechgard salt type systems. Okay, so this was a single cube. So what happens for many cubes? So there are different techniques to pull out the single cube physics from this one can call a mess, which is a response from a full array of tubes. And these are two different kind of approaches. One is nothing else that the reconstructing of an image from a projection, which is what routinely done in CAT scans in medical. So this is one of the types of the transformation, which is called inverse Abel transform, which applies to a cylindrical systems with cylindrical symmetry. And if you don't have this symmetry, there is a generalized form, which is called the Radon transform, but then you need many different projections of your system to reconstruct a full 3D image. While in this case, single projection, which is, so they are shining a laser field and they see a density profile on a screen. So single projection is sufficient because there is a symmetrical symmetry. So then one can reconstruct 3D, and then one can really go and see what happens at the center or in different positions. Another way is to use the LDA, and one can really check that if you have harmonic trap, and if you do the derivative of the axial density, actually you can pull out the density profile of the central tube. But all of them actually involve some kind of derivatives, and these are prone to a real high noise, because this is the some noisy data, which is a trouble for them. But so they are able to overcome this somehow, which I'm not really an expert on this, but experimentalists are somehow able to do this. So what about pairing? So I was telling you about that in a single tube there is no long-range order in principle, and all the correlations are power laws, so that's what it is. So if one has many tubes and one allows now tunneling between these tubes, so if one has the pair tunneling, which is Josephson tunneling, it appears to be a relevant perturbation, and one can see that the system actually will support the true long-range order, which if one tunes in a regime of 1D systems, one can probably convince, just looking at this paper, it's oneself that this true long-range order will be of this FFLO type. So one can really tune from 1D physics to, let's say 3D physics, simply allowing the tunneling between particles. So this is about fermions. So I'll try to change a little bit gear and talk about some BC in a trap and the disorder. So what happens when those all this thing comes together. So there is an experiment at Rice University, which I'll try to describe. So what it is an experiment on so-called dump dipole oscillations, where I'll claim that interactions, confinement, and disorder are really crucial to understand this experiment. So what it is, so this is a BC. Okay, sorry, I forgot that the before experiments were on lithium-7, which are fermions. Sorry, lithium-6, which are fermions. So this one is on lithium-7, which are bosons. So this is a BC made of bosons. And what experimentals are doing it, they have it in a trap, and then they move the trap, let's say here, and applying the random potential on top of it, and then they see how this cloud oscillates. So this is basically center of mass coordinate of a cloud as a time, as you see, from 0 to 6.7 seconds. And then one sees some kind of a nonlinear damping of this mode. So how the disorder is applied? It's basically nothing other than the random intensity laser field which one creates by passing the laser field through some diffuser glass, and then on the screen or on some particular space you focus and you have some random field. So it's basically a similar technique as one uses for optical lattices. Simply it's a random in this case. And so the dots are experiments here, and blue is basically a guide to the eye. So the green and blue, both of them. So again, this is a center of mass coordinate as a time. As one sees, there are some different, so it's a nonlinear damping, as you see here. And also there are some different regimes, in a sense that there is a weakly damped regime. Here is also kind of weakly damped regime, and the strongest damping is in some intermediate regime, in this case. So that's what we are trying to understand. Why are different timescales in the system? Yes?
So in principle, I guess the interaction should also cause a collapse.
Sorry?
The interaction between the atoms should also cause a collapse?
The interaction is positive here. It's a repulsive interaction between bosons.
Cause a collapse anyway.
I mean, if you have in attraction, then there is a
instability
and you get a collapse.
Oscillations in the trap?
The center of mass oscillations.
It's a center of mass.
Yeah, but they should still...
No, it's for interacting in particle systems, you still have center of mass oscillations as
Yeah.
perfect modes.
Yeah, but after a while it will spread out, and then you can have revivals as well. If you have only-
Probably, I'm not really sure, but at least in this time scale, that's not
I think in
what is
the
not
time
happening.
scale it won't be.
Yeah.
Ah, okay.
So you are saying about some quantum revivals and those kind
Yeah,
of
in
things?
principle you have a non-linear term and you have a Newtonian, and then
Yeah.
it leads to a collapse, and then you will have revivals later on.
But you see, okay, I will describe it, but we'll see. Thank you. So what one can think about, so this is some kind of a sketch, what will happen. So we have like perfect condensate and you shift it and then it starts oscillating in this potential. And so what could be the sources for the energy dissipation? So this central mass motion is, so what we think is transferred to some different type of excitations, and what can really be a culprit here. So there are of course the Bogoliubov modes of the VEC, and there can be usual. I mean, depends on if it's zero temperature or non-zero temperature. You also have thermal population of those modes, and would be solitons. That's other question here, because some people are reporting the realization of these solitonic states in this kind of systems. So what we don't go that far, and what we assume here is that we have zero temperature, and we will go to Bogoliubov, usual Bogoliubov regime with non-interacting quasi-particles, use local density approximation again, and data correlated disorder. And we will try to understand whether we can somehow reproduce this nonlinear damping scenario in the system.
What's the length scaling experiment for this disorder compared to a trapping scale?
These are, I mean, this is much less,
Okay.
definitely. I'm just, I can give you exact numbers, which I don't have. Okay, so what you see? Okay, so this is about the center of mass modes we were asking. So one basically starts from the standard Hamiltonian, which is, this is the potential, which is harmonic in this case, and the interactions. And one can derive the hydrodynamic equations coming from that, which are those which basically govern, these are the continuous equations for density and the velocity, basically. And one can solve it, and one sees that it supports different modes with different frequencies, which are labeled by the radial and the angular quantum numbers. And the dipole mode is nothing else that, S wave type with L equal to 0 mode, which has the same frequency as the trap. And what is interesting here that those frequencies are interaction independent. So that's something really very amazing. I think that's probably only happens in the harmonic trap, which perfectly decouples relative motion with respect to the center of mass motion. And what we are saying here that the disorder will be the mediator, which will couple those different kind of modes, this center of mass motion modes with the B, like Bogoliubov type excitation modes. So how one can treat now the disorder? So there are different methods, but one of them I will just briefly tell you. It's a replica trick. So let's say that we have this disorder potential here defined with this correlation, alpha correlated, as I said, with some strength.
So excuse me, you don't consider shape instabilities of this cigar?
No. So it will be, I mean, it's basically coming from the simple-minded, simple-minded theory from the experiment. I don't really see nothing happening from the experiment.
No, it's a hydrodynamic mode, so it also includes, this
yeah, but those are much higher energy ones.
Well, bending instabilities actually have much lower frequencies because it's k squared, not k.
But I'm not sure whether they are actually excited in the system, so yeah, that's a valid point. I'm not really don't have an answer on that. So, and then one can basically do if one wants to do the quantum averaging, one needs to take an average of with this particular probability distribution, let's say. And then there's a problem of defining the full average, which is a quantum average plus the disorder average, because you have this denominator from the quantum average, which you can't really divide average by average, because it's the one you should average the whole thing. And to avoid this denominator, one introduces, let's say, many replicas of the system and writes this exactly by this in the limit of n is equal to 0. So you basically get rid of the denominator and then do the averaging more nicely, because you don't have the denominator anymore. But then you need to take into account n is equal to 0 limit, and also the price you pay, it will be the interaction between different replicating modes, which is not a very complicated in a sense. Because it will, in this case, it will introduce another 4 boson terms which are already present in the system. So it will be similar type terms. So let's see what we have in the let's say relative motion degrees of freedom. So these are the Bogoliubov excitations with the energy here and the standard transformation from this is a condensate mode and plus all the excitations. So this is standard, the Bogoliubov modes. And what we were saying here is that this disorder will start coupling this dipole mode with those excitations. And what one can really do here, I can't really, don't have much time, I can't really go too much detail, but what we'll do is to take into account the disorder using perturbation techniques. And one can really go and do some, the diagrammatic calculations. But what is actually interesting here is that already on the second order, there is possible to fairly well describe the system with effective coefficients. I will describe that later. So what we do is basically calculate the imaginary part of the self-energy, which gives you the transition rates between the different modes. And this is basically, after do some manipulation, this is the energy decay per unit time, basically. And there is an interesting piece here, and this is coming because the condensate is moving, and in the moving frame, one is to correct for those Bogoliubov energies, and this is nothing else than the Landau criterion for the BEC. So if one wants to generate Bogoliubov modes, one needs to overcome, or at least be, the speed of the cloud should be more than the speed of the sound, or in this case, so this usual Landau criterion, so you need some kind of critical velocity to start exciting Bogoliubov excitations. So in this case, one has a linear spectrum, and that criterion is fulfilled. So if you would have the quadratic spectrum, then you would not really have superfluidity in a standard sense. So in this case, it's a linear spectrum. There is no Roton minimum or anything like that, as in usual superfluids of helium, but it's still, there is a Landau criterion here because of the linear spectrum. So what happens? So this is basically how this function behaves. So let me show you how this function behaves. So what we assume here actually that, so the excitations are only on the long axis, and that's because from the experiment we knew that it was really, with a large aspect ratio, and we basically it's an approximation to allow only transverse excitations, and also there is no condensation deflection in our case in principle. So we say that our condensate is large enough that those particles which will be excited, they won't really change the number too much, which I will go back to it. So this is again the same function, and you see that as a function of the velocity of the cloud with respect to the velocity at the center of the speed of sound at the center of the cloud, there is this log-log plot here, and you see that this function actually has some kind of different features. At low velocities, it has one type of behavior, and for larger velocities, it's different type, and there is some kind of a peak here, as one can say, for velocities which equal to the speed of sound at the center of the trap, which is basically says that it's that is actually the velocities where the most of the dissipation occurs, which actually coincides with the Van der Waals theory. And from this one can really basically define an equation for peak velocity, how peak velocity changes with time. So it will be basically looking at how this curve, its envelope behaves. That's what we're interested in. And so if you do this, so you have, in our case, because we actually use the local correlations, so delta uncorrelated gas, our this gamma is actually some kind of a free parameter, because in real experiment these correlations are not delta correlated. And this, in our case, it's nothing else than the fitting parameter for our theory in this case. And that's what we are doing. We are fitting to the experiment, and this is the fitting. So this is our experiment again, these dots, and this blue line is actually fitting. And this is the point where the velocity of the cloud is the same as the speed of the sound at the center of the cloud. So this is basically some kind of maximum dissipation place, one can say. And one can also pull out how this dissipation, rate beta changes as a function of the interactions. So this is a scattering length for smaller and larger velocities, and one can, this is experimental graph which also has beta as a scattering length, and one can say that it, if not exactly the power loss, but at least trends actually are correctly reproduced. So what we have here is the simple free parameter is gamma, and what we see that interaction actually effectively reduces the disorder, because the gamma, what we are getting from the fitting, is actually weaker than you could think about from the experimental values. So that somehow tells you that interactions, which usually tend to diminish disorder effects, that's actually what happens here. And if I want to take into account finite size of the disorder correlations, one can do it, but it looks like do some more quantitative corrections, so some details, but qualitatively looks like it is reproduced. Yeah, I think that's, I'm almost done here. And let me go to the conclusion. So what I'll be describing is different strongly correlated regimes which can be realized in using ultra-cold atoms, mainly low dimensions, I was telling you. And for fermions, I told you that one can, for fermions and positive interactions, that is repulsion, one can realize different Laffinger liquid regimes depending on basically where you sit in a trap. And one can also measure density-density correlations and can distinguish between those different points, different regimes. And on the other hand, if one considers interplay of spin imbalance and negative interaction, which is an attraction in this case, one can characterize system according to the pairing, and one can see different pairing phases, and also look at the stability for finite temperatures to really be able to understand different phases of the system. And then I was telling you about how one has a scheme to determine the phase diagram of a uniform system if you have the thermodynamic density profiles of a trap coming from experiment or from theory. And finally, I was describing trap DC oscillating in a trap with disorder, and the main thing to take home from here is that it's important the interplay between interaction and disorder and plus the finite size in this cloud, which is very important to have these different time scales of the dissipation. And which is remarkable is that even with some kind of simple-minded theory, there is some agreement with the experiment, which is interesting and nice, I think. So I'd like to acknowledge some people at Rice University, especially Randy Hewlett's group, and some funding sources which provided some support while I was doing this work. Thank you very much.
Questions? Any questions? The speaker? Thanks, speaker again.
There were some questions.
Huh?
There were some questions.
I would like to still ask one question. I mean, this Rice experiment, I mean, that was purely 1D for fermions.
The fermions, yes.
Okay, but no 3D.
No, as far as I.
Okay.
So aspect ratio is more than 400.
Sorry, more than?
Aspect ratio is more than 400.
Yeah,
okay.
but it's really high. I mean, it's in the transverse direction. It's basically set by the wavelength, which is 1,000 angstroms or something of the laser field. So it's like 500 angstroms is the lattice spacing, where the size of the cloud is of the tens to hundreds of micrometers. So these are the aspect ratio.
Is it possible to tell in those experiments if there is just some coupling between these cigars?
I mean, I would say that the interesting thing is I was telling you this distinction between 3D and 1D, that there is different kind of regimes, center of the trap versus the edge of the trap. That thing should show some signatures already. I think so. And one more, it would be somehow to do some experiment which measures overall coherence of the cloud. You see, then that would be to see whether there is some kind of superfluid regime in there, which usual things are, people try to rotate them or try to see vortices or those kind of things, which is interesting with these spinning balance systems, which I don't really know if there is much of theory on those.